Okay, I'm going to do it gradually. So first even though you can't see this here, I'll move it up in the end when we get here. Okay, so first let's just focus on this part here. So this part here that I'm showing here is actually not so different. So I'm going to go back and forth between what changed. Okay, so this is the slide we had in the morning before, where we calculate this equation and this equation. When I go to the next slide, see what changes. So it's just a definition change. So I define this thing called xij, which is equal to xi minus xj, and I define this thing called g, xij, which is a function that represents this 1 over xij part. And so when I write this like this, then this here changes to just g times qj. Of course, this is, because qj was being multiplied to this thing, this is equal. So, but it's important to write it this way because otherwise this part is going to be very, very long. So I've introduced a abbreviation for the equation so that this part doesn't become too long. Okay, so that's all I did. I introduced this notion of xij, and I introduced this notion of g here. And then this part here can also be written with g, xi prime, j prime, and times qj prime. So this is, and these two parts remain the same. Okay, so now what we do is to achieve higher accuracy, we're, instead of just summing up everything and just saying everything is equal, instead of doing these two very crude approximations, we are going to introduce a proper mathematical high-order expansion based on the concept of Taylor expansion, which you don't see right now very clearly, but I'm going to move this up in a few more minutes. So first, focus on this part here. What I'm doing is I'm saying that xij, the vector that goes from j to I, can be broken down into three vectors, xi to xi prime, plus xi prime to xj prime, and then xj prime to j. This is basically saying one big arrow from j to I has been broken down into three arrows of these two. And it's just vector addition, where if you add the three arrows, it becomes what's connected from the end to the beginning. So that's this equality here. And now we introduce this concept. This is important when applying the Taylor expansion, that these two arrows from j to j prime, this one, and I to I prime, the sum of these two vectors is smaller than this long vector here. This is a condition for the Taylor expansion to converge. So say that we have these two boxes far enough. Every point in this box is inside this box. So the vector can be at most the longest from here to here. That's the longest, maximum. Here also, if the j is at the corner, this is the furthest. It's at least this size. But this arrow here is very long compared to this longest xj prime and j and I prime and I. So we can say that the sum of these two is much smaller than this. Or actually, this is the condition that we need to apply for the following to converge. Now we move to this thing. So I'm going to move up the slide a little bit so that you can see this. Okay, so what was shown here is a standard Taylor expansion. The function fx can be written as a series of the derivatives of the function f with respect to a, some value, when subtracted from x gives you a very small number. So this part being small is the important thing here. If this number was larger than 1, then this, because you keep multiplying by n, this number is going to get bigger and bigger. If this is x minus a is smaller than 1, if you keep taking or taking the power of n, then it becomes smaller and smaller, right? So it depends on whether this part is smaller than 1. So this part needs to be small for this thing to converge. And so if you think of x as xij, and if a is xi prime, xj prime, I prime, j prime, then x minus a is this minus this, which is according to this equality here. It's the sum of these two things here. And so this part being small, now you see the reason why this had to be small. It's for this Taylor expansion to converge. This part had to be small compared to this part here. And now, if you just apply, since Taylor expansion has this power of n, factorial of n, you have this here, and then this derivative of f is shown in the vector form, because we're dealing with not just a 1D function here, because x is a vector. So in 3D, this is also has x, y, and z components. This n will also have x, y, and z components. This nabla here will have x, y, and z components. So it's this n power here is actually like a partial derivative of x, y, and z. But so when n is 1, it's like partial derivative of x, partial derivative of y, partial derivative of z being applied to g. When n is 2, it's like x, 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 y, x, z, and then y, y, x, y, x, y, y. So it's all of those derivatives. So the number of n just represents the total of the combination of the number of derivatives of those different components. So view this as a vector form of the Taylor expansion. That's the simplest way I can put it. Think of this as the 1D Taylor expansion. This one is like a 2D or 3D Taylor expansion. It's this exact same thing here. It's a 3D version of it, but so f becomes g, a becomes xi prime j prime, x minus a becomes xi prime, xj prime j, and the powers of n's and the factorials of n's are vectors. In 2D, they have 2 components. In 3D, they have 3 components. This sum also, this n is also a vector. It has 3 components, nx, ny, and nz in 3D, and it's summing. But if you sum to infinity, you get the exact answer. So gx can be written like this. So this is an important thing you want to remember here. This is an important change that you made, is that g can be written using Taylor expansion. This is like high school math, except for that if it's in 2D or 3D, it's more like university math level. But it's just Taylor expansion, nothing difficult. You applied Taylor expansion to function g by decomposing xij into these 3 arrows and saying that these 2 small arrows are much smaller than this big arrow here. That's all. Just Taylor expansion. And now, I'll move back the slide because I don't want to break the original picture. Oh, sorry. Okay. Now, let's go to this side. So, it's the same equation as here. G and the Taylor expansion, except I changed the infinity to a finite number p. So what does this mean? It means I'm just truncating at p, because I can't do this on a computer. I can't sum to infinity. On the computer, in the actual program, you need to stop at some number p. But the good thing is, if you increase p even inside your code, you can actually get enough accuracy, because it's just controllable. If you want more accuracy, you can just keep increasing p, and eventually it will get to like double precision round off error, which the computer can't be more accurate than that anyway. So you just need to increase p until it's sufficient. Usually in many applications like molecular dynamics or fluid dynamics, astrophysics, you don't need that much accuracy. You don't need like the full 15 or 14 digits of accuracy of double precision. You can actually get away with maybe 10 or 8 or even 4 digits of accuracy. Then this equation here, we apply only one more mathematical formula, which is the binomial theorem. This is also high school level math. If you have x plus y to the nth power, this can actually be written in this combinatorial form between x and the product of x and y to these different powers. So it's, sorry, I'm missing a summation here. There should be a summation from like k going from 0 to n here. But the summation is here, so even though this part is slightly incorrect, this one is correct. So what we did is we applied this binomial theorem to this part here. So xii prime plus xj prime j to the nth power can be written as from here, starting from this summation up to here. So it changed into this term here. Everything else is the same, as if you can compare with your eyes. This part is the same as this part. This part is the same. But you changed this part using the binomial theorem, very simple mathematical theorem, to this part here. It's identical. N power, n minus k factorial, and k factorial, x and y are n minus k and k power. So it's the exact same thing. We just applied this theorem. So this is equal to this. Everyone agrees? Okay. So now the rest is even simpler math. So we have n factorial here in the numerator and in the denominator. So we just cancel those two. That's this step. Everything else hasn't changed. The next step, we swap the loop order between n and k. So here, we had the summation over n here, but now we switched the order which we do the summation, which has an effect on this because we were summing to up to n here. So if we move this forward, actually we need to change the number from n to k going to p, because so say that k is 0 here, k is 0 here, and then you are originally summing from 0 to n, which is now, if you take this outside, then if you look at it the other way around, n was going from k to p. So you're actually, this part isn't changing. There's nothing on this side that changes. It's just when you swap these two summation orders, you have to change the number which n goes from. It goes now from k to p. So think of this as a triangle. It's like a lower triangle summation. So n goes from 0 to p and k goes from 0 to n. So if you view this as like a, in the form of a triangle, it's very easy to see this correspondence. So when k goes from 0 to p, then now n would look like it's going from k to p because of the triangular effect. If both went from 0 to p, it would be the full square. So it's like a lower triangular loop because this was only going to n, the diagonal component. It wasn't going past the diagonal. But now, since it's not going past the diagonal, you have to start from k. That's the sort of the triangular loop you can think of. Okay, now, once you were able to picture that triangle, you can see that these two loops can be swapped. Now, you just redefine n minus k to n. So everything here that was written n minus k is now, so see this n minus k, it turns into n. K just remains k. And the n minus k here turns into n. So if n minus k turns into n, what does n turn into? N turns into n plus k, because basically you're just adding k to n. So this turns into n plus k. So now it's just a redefinition of variables. Without loss of generality, you can do this. So And we just changed n minus k to n everywhere in this equation. So this whole equation changed to this one. Now we're almost at the end, and the end is significant, but again, you can't see the bottom, so I'm just going to move this up slightly, like this, so that you can see the... So now we're here, and then what we do is we just move certain things around. So this is a loop that concerns the variable n. It doesn't concern k. So we can move k in front of this summation, because this is only a summation over n. So we can't move n past this summation, because actually this summation is operating on n. But k we can move here. So k is outside now. This x to the kth power also can move outside, because this summation doesn't concern the k. This one does. So we move k up here. Also, in a similar way, we can move this n all the way to the back, like this, and then we can move this power of n all the way to the back to make it look like this. Now, this form, if everyone agrees that this has turned into this with very simple mathematical manipulation, no like advanced math involved here, binomial theorem, canceling, just redefining variables. So like a very basic undergraduate level math can give you this equation here. The significance of this is this term here being multiplied with q, because this is g and we multiply q to g. If you multiply q to this term here, it's actually the definition of the multiple expansion. This is what a multiple expansion is. Multiple expansion is a power of the distance between u and the center of the cell, which is j prime j, this vector here. It's a power of those. So multipole comes from the word, the original terms are like monopole, dipole, quadrupole, and a plural are having more than one pole is, where the word multipole comes from. It's like multipole. And so a monopole is when n is 0. When n is 0, it just turns into q, because the factorial of 0 is 1, and a power of 0 makes this 1. So this whole term turns into 1, and you're multiplying by qj. So the monopole is the value itself. So this is actually a monopole, if defined. And a dipole is when n is 1. So if you put 1 here, this part is 1, and then this part becomes a power of 1, so it's just x. So without this thing, it's just x. So you multiply q by the vector x. So in 3D, it has components x, y, and z. So it's x times q, y times q, z times q. Those three values are called the dipole. So n equals 1 gives you the dipole. N equals 2, similarly, gives you the quadrupole. So these are called multipoles. That's why I wrote here m. So multiplying this by q gives you the multipole expansion. Now, in FMM, you have another side of the term, which you use for this side. So the multipole here turns into a local expansion here. So multiple expansion on this side turns into a local expansion on this side. What that calculation is doing is actually doing this part. It's taking this m and multiplying it to this gradient of the g function here. And if you sum all that up, you get something that's called a local expansion. So this term here gives you the local expansion. Once you get that, you multiply that to this part here, and then this gives you, since this is g and q you've multiplied in the beginning, once you're done with this whole thing, it actually gives you the u. So I'll show in the next picture the actual correspondence between the original thing that I was describing and how that is the monopole. So what I've described in the first lecture this morning is actually something called a monopole. And so this whole equation here can be turned into this one here. And so when you have these terms, the accuracy is limited because there's nothing you can control. But we've shown here that this is the multiple, and this whole term is the local expansion, and this term here can be used. So now we apply that. We swap this thing, and this thing with each of these terms that we've shown here. This, maybe I should shift the picture up again so that you can see. Okay. So now you can see everything. So this one has turned into this, like I told you, this term being multiplied to q is the definition of the multiple expansion. You do that for all the points inside this part here. So you're summing for everything inside this box. And then the result you get, so because you have n terms, I'm writing here m to the nth power. So when m is 0, see what happens. This part becomes 1, this part becomes 1, so you get q. And then you're summing that over the domain, which is exactly this thing. So m0 was actually qj. So according to this mathematical definition, this was just calculating the first term of what we're going to do for many terms now. So you already were doing the first term. So you can think of this basic algorithm that we described as the case when n is 0. So it's the same algorithm, but when it just so happens that when you put n equals 0, it turns into this one. In a very similar way, step 2 here is actually the case. So we write here this L part. It's the same equation I wrote here. You're multiplying by the m. So since we already have this in the form m, we can just use that m to calculate this part. So I'm just multiplying this by the m directly. And then the answer I'm writing as L. And this is a function of k because we have k terms here. And we're just summing over the n terms of the m for each term k in the L. So it's a double loop of n and k. But we have this whole equation, if you think of it, when we say k is 0 and also n is 0, see what happens. This whole part, because these are 0, 0, and this is zeroth derivative means you don't take any derivatives, so it's just g. This whole part becomes g. And then because m0 was q prime j, this turns into the original thing, g times qj prime. And this whole summation, because we're assuming that p is 0 and k is 0, so there's no summation here. So it just reduces to the original thing. So L0, now you see that it's equal to ui prime. So we were already calculating the first term, the 0, when n was 0 and k was 0 and p was 0. This reduces to the original form. Again, here, the last term. Now that we've calculated Lk, we just use that and we add it to the rest of the equation, which gives you, the ui. So now ui can be expressed as this term. We have already calculated Lk. And again, see what happens when p is 0 and L is 0. So L0 was ui prime. And then these are 0, so these terms go away. And p is 0, so this summation goes away. So it's actually saying ui equals ui prime, because L0 is ui prime. So it was doing this exact same thing. So this form reduces to what we were doing. This is actually a first term of this expansion, the Taylor expansion. So we're simply increasing p and increasing k and increasing n here to get the rest of the terms. So we were just truncating early here. It wasn't something that was done artificially. We were actually correctly doing the first term of the more proper mathematical form that has higher order terms. So if you just want more terms, now you have to calculate this summation for n that is larger than 0, and a p and k that is larger than 0, and then this will become closer and closer. So this g will become closer and closer to the correct g value, because as you increase the truncation order, p, to higher and higher numbers, this becomes a more and more accurate approximation. As long as xi prime j prime is larger than the sum of xi I prime plus xj prime j. That was the condition. That was the condition we saw earlier when we first introduced this. Where did we introduce this? Here. So this was the condition for this Taylor expansion to converge to begin with. So this, as long as we have this, the accuracy is controllable to whatever we want. So by just simply increasing more terms here and more terms here and more terms here, we can get, infinitely accurate solutions if we can use high enough order arithmetic operations. We can get any accuracy, because we can just keep increasing the order of the Taylor expansion. So in short, this is just Taylor expansion. So multiple expansion and local expansion in the end. So these abbreviations stand for particle to multiple, multiple to local. It's very clear from the naming and the correspondence between what you're doing. You're turning M into L, and then you're turning L into a particle information, so L to P. So you're actually doing a very simple Taylor expansion, and that is at the heart of the math in fast multiple methods. It was just Taylor expansion, and you were already doing the first term with this simple equation. Now you can do any order expansion by doing this. So this is just one level. So when you actually program this, now you are doing this between this blue box and red box. You do these three steps, P to M, M to L, and L to P, instead of doing this one, and this one. So we'll do this gradually in the hands-on. We'll first start with this one, but you can start from that same code and just change this into this, change this into this, change this into this, and the accuracy, you will see that will automatically increase and will be controllable. If P will be a variable inside your code, you increase that from 0 to 1 to 2 and see how the accuracy increases. This is an interesting test that you can do. But mathematically, there's nothing too complicated about fast multiple methods, because when you try to read about fast multiple methods, especially the 3D variants, they first start from spherical harmonics. This is like more advanced math. But actually, all you had to know to understand the concept itself was Taylor expansion and maybe binomial theorem. So it wasn't very, these spherical harmonics or complex numbers in 2D are used. But the basis is this. You can start from, this is probably the simplest way to understand at least the basics of why you can expand and, what are the conditions for it to converge. So now we move to the multi-level case. So remember, we had a case where we have more than one level. We had to move from here to here to here to here to here to here. So how do we do this intermediate step? We need to change a multiple expansion of these boxes into another multiple expansion for a bigger box. So to do that, we make a new decomposition into 5 vectors. So we originally had 3 vectors that go from xj to xj prime to xi prime to xi. Now we have 5 vectors that go from j, j prime, j double prime, and then to I double prime, and then xi prime, and then xi. So this double I prime, double j prime are, you can think of the double primes as the previous I prime and j prime. They were at the center of the big box. But now we introduce this intermediate smaller one. And now we can rewrite that equation we had that defined the multiple and local expansions. Instead of using I prime and j prime, I'm using I double prime and double j prime. It's just switching the prime with double primes. Starting from here, I can do the following. So now I decompose j double prime j to j double prime j prime j. So it's just decomposing this vector into 2 components, this sum of these 2 arrows. By doing that, this mj double prime term here that I had, this one is mxj double prime, this term here. This can be rewritten as, instead of j double prime j, I'm going to write it as j prime, j double prime j prime, and j prime j. So these 2. Again, when we have a power of something that's being added, we use binomial theorem. Again, so now it becomes this combination thing with the summation from k to 0 to n, and then these 2 powers of these 2 terms. Just simple binomial theorem. And then this, again, we cancel the n prime, and then we get this thing. If we look at this thing closely, what is this doing? This is turning a multiple expansion at j prime into a multiple expansion at j double prime. This is what we wanted to do. We wanted to turn this multiple expansion here into a multiple expansion for the bigger box. Now we have this. Because this definition, by definition, qj times this kj j prime j to the kth power. This is, and taking this k factorial here. By taking these 3 things, we can make it, we can call that mk. This is a multiple expansion for j prime. And now, similarly, we take this side, decompose xi I double prime into xi I prime, I double prime, this thing. And then now the ui term, this part that we had for this term here, this one turns into the sum of these 2 vectors, which again, if we use the binomial theorem, turns into something that looks like this. Okay, yeah, so we already canceled the k prime term. So it did it in one step. And now we have this thing here. We swap the order of the n summation with the k summation. We swap the 2 again. The same thing we did before for the multiple to local part. And then with this term, so this will be equal to this if ln was this thing here. So if we make this whole term look like this shape, which is what we want it to turn into, we want it to become this, then ln is equal to all these parts here, which is this thing here. So now, what is this? This is a way to turn the local expansion at xi double prime into local expansions at I prime, these small ones. So now we have what we want. We have a way to turn this into this, this into this, this into this, this into this, this into this. So now if we make that into, we swap that, we have this, and this, and this, and this, and this. Now we have the full hierarchical, all 5 components, P2M, M2M, M2L, L2L, L2P. All these kernels we can do. And again, all we used was like binomial theorem and swapping loop orders. So it wasn't anything complicated. And now we can describe the full FMM calculation. And basically now you can code FMM. If you can code the tree structure to manipulate these cells properly. But the mathematical part, you understand now. The remaining thing that might be complicated is how to calculate this derivative, the high order derivative of the g function here. That may be the only difficult thing to do, because these are basically factorials, multiplications, taking the power. These you can do very simply inside the program. The only difficult thing remaining that you have to do is this thing. But there is a mathematical formula that creates a recurrence relation to calculate higher order derivative terms of g. So I'll explain that to you maybe tomorrow when we actually try to code this thing. But today you don't need to worry about this. Just understand where it comes from. This g, using Taylor expansion, turns into this long form where it has the multiple expansion and then local expansion, which gives you the end result. And you can, by using binomial theorem, you can construct operators that turn multiple expansion of smaller boxes to larger boxes, and local expansions of larger boxes into smaller boxes. So with all these operations, the only complicated one is probably this part here. Okay, so now you have the multi-level equations. So this is the entire flow of calculation. For the whole FMM, now you understand the math somewhat. So it's easy for you to grasp the picture now, I think, in a very concrete way. So first you have all the particles. These are your sources. You want to calculate the effect of all these points onto all the other points. So first, what you do is, for all boxes, so first you divide the tree into smaller and smaller boxes recursively. This is what you do first. You divide the domain, you cut it in half, and then half, and then half. And then at the bottom, if you reach a constant number of points, you can set a criteria, like if one box contains less than 32 points, I stop dividing. If you do that, then you'll reach a bottom of the tree like this. Then at the bottom, for each smallest box in the tree, you do this calculation here. So everything inside there needs to be summed according to these factorials and powers of x. Between the distance between, so j prime in this case is the center of your box, and j is all the points inside that box. So this vector should be small. This number should be at most the distance from the center to the corner of your box. And then you just sum that up for everything. Okay, so this is like a whole view of the whole calculation. You don't just handle one box against one box in this case. You want to handle everything here. So you preemptively sort of calculate everything, because eventually someone is going to use your multiple expansion. So why wait until it's being used? You can just calculate all the multiple expansions because you know someone will use it in the future. So you calculate everything for all of them, and then in a similar way, you go up one level. What you do is you take the center of the small box, and then you want to calculate the multiple expansion at the big box using all the small box centers, or the multiple expansions at the center of the small boxes. And so you do this calculation that we derived using the binomial theorem. You use this thing to calculate the multiple expansion at the large boxes. If you have a deep tree, you keep doing this, going up the tree, up the tree, up the tree, and you do this over and over again. So if you're in 2D, you have always 4 boxes to sum up. If you have 3D, you have 8 boxes to always sum up. If the points, so say that these particle distributions are not uniform and you have a big hole here. In that case, this number won't always be 4 or 8. Some boxes will be empty. So as you go up the tree, you'll have cases where this sum is like 7 or 6 or even 1 in some cases. So you do this anyway. It's the same calculation, even if there's empty space. You just keep doing this calculation going up and up the tree. Once you reach the top, you have all the multiple expansions, m, at all levels and all boxes in the tree. So your tree is full of multiple expansions now. You have a full tree full of multiple expansions. With that information, what you can do is, at the high level, you can calculate the local expansion of this big box using the big multiple expansions that you have at this level. Going down one level, you've created the multiple expansions for all of these boxes, but you don't use these ones. You've calculated these ones out here, but you've already calculated the effect of this gray part at this higher level. So you don't need to calculate the same effect twice. So you skip this part, skip the white parts. You only use these red boxes to calculate the effect of this blue one. Of course, if your blue box is somewhere else, then you might use these. So it's not like you've wasted these multiple expansions. Someone will use them. It's just not this blue box. This blue box will only use these red boxes. And then you do this blue box so this blue point needs to loop over all these boxes. And then for each blue box, you need to find the appropriate red boxes to interact with. Same here. For each blue box in this whole domain, you need to do the same calculation that is shown here. So it's not just this one blue box. It's just in this picture, I'm just showing one blue box, but you do this for all the boxes. And then here, at the bottom level, there is always a white part that remains where you can't approximate using this equation here. There, you use the original equation and just directly call the particle-to-particle interaction. And then you get the part of the solution directly for ui. And you keep summing to ui, the effect of here. And then you need to sum to the effect of ui that was given here. You need to sum it with the effect of this and this. So how do you get the information from these large boxes? You just cascade down the information. So the information from this big box goes down to this smaller box. And then this goes down to a smaller box here. And it gets summed to the information that was calculated here. So as you're going down, you need to keep summing with the other effects. So this blue box turns into this blue box here, and then this blue box gets summed to that effect. And then this is all being done by the local expansion being transferred to the center of from the bigger box to the smaller box. Bigger box to smaller box to smaller box. And then finally, when you're at the bottom level, you need to change this local expansion at the center of the smallest box to actual particle information. So then you just calculate this equation here and then sum it to the ui at each individual particle. And then that gets added to the effect that you calculated here. So you need to actually sum, by doing the summation of this guy with this guy, you're actually summing this gray part effect to the effect of this gray part to the effect of this gray part. You're summing everything up. So in the end, if you do all these calculations correctly for all the blue particles, not just the ones shown here, but for all the boxes, all the blue particles in all the boxes, then you will get the calculation of everything against everything. And your calculation would look, your data dependency would look like this. So it goes from up the tree, and then at this level, the yellow boxes interact somewhat with each other, crosses over, and then goes down the tree. And then in the background, you sort of have, for the near boxes, you have a direct calculation against points. So this is shown in the gray lines. So that's this gray part here. So you sort of have 6 different equations to calculate. 1, 2, 3, 4, 5, 6. And for different combinations of boxes. But programming-wise, all you need to do for all of these calculations is first find the box which interacts. So for this one, you need to find which box, and then which particle is inside that box. For this one, you need to find this box and which are its children boxes. For this one, you need to find, for all the boxes, you need to find these gray boxes. Actually, finding these gray boxes is the most difficult part for finding the boxes. Now, going down the tree, you just need to find your children boxes and move the information down. And at the bottom, you just need to find, again, all the particles that belong to your box. So mathematically, you need a way to calculate all these equations. The most difficult part being probably to calculate this gradient of the g function here. But sort of programming-wise, you need, the most difficult part might be how to calculate these gray or how to determine these gray boxes. How to sort of grab that information from, so you need to have some scheme for identifying far boxes. So I'll describe that in tomorrow's lecture. So tomorrow will be on tree construction and interaction list finding. So these gray, the list of these gray boxes is called an interaction list because it's a list of boxes that interact with each other. So construction of the interaction list is also a critical part of an FMM algorithm. But I will cover that tomorrow. So today, you just have to remember, FMM consists of, this is the whole picture. You now see from sort of a high view, high order view, how you can increase the accuracy using these expansions by increasing the expansion order. And you just need to construct a tree structure so that you can hierarchically sum all the multiple expansion information, calculate the local expansion from the interaction lists, and then cascade down the local expansions, and at the bottom, calculate the potential from the local expansions. So this is the whole picture of the FMM. And I think, is this my last? No, I think this is my last slide. So now I'm going to give you some timing results for an actual run. When you actually run this, so you have the P2P kernel, P2M, M2M, M2L. So say that you run all these things, and you increase n, the number of particles. So you start from like a very small number, and you go to like 10 million. This is 10 times 10 to the 6th, so it's like 10 million particles. And then this is a very old result, so it's taking a very long time. Now I can do this in like a few seconds. But just for the purpose of explaining, it doesn't make a difference what the absolute value here is. What's important is the color. You see that this M2L that's shown here, this part, or either this part, or it's usually at the bottom level. You have many blue boxes that need to interact with all these red boxes. So the M2L calculation at the bottom level is usually the most expensive part, which is shown in this yellow. But it's not always the most expensive part. So say you had 4 million points. Actually, the yellow part is rather small. It's this P2P part that's big. So think about why this is. So why for some n is this part big, and why for some n is this part big? So this is the key to understanding how to make this calculation order n. If you draw order n line, although this is wavy, the order n straight line will fall, it will follow the order n line. So what's the key here? So the first thing to know is this P2P, when you increase n, the number of particles, without changing the level of the tree, what happens? The number of particles per box increases. When the number of particles per leaf box, let's call the boxes at the bottom of the tree the leaf boxes, because the limbs of the tree are leaves. So when the number of particles per leaf box grows, then this calculation, since it's an n squared calculation, grows as n squared. So you see this will, form a parabolic line, like a n squared, or like if you draw y equals x squared line, that's what it would look like. Because it's growing as n squared, it will keep growing quadratically. And then, so at some point, it becomes beneficial to divide the tree. But if you divide the tree too soon, what happens when you divide the tree one level? Actually, since one box splits into, in 3D, 8 boxes, in 2D it splits into 4 boxes. Since it splits into 8 boxes in 3D, the number of M2L calculation suddenly jumps 8 times. So this is what's happening here. The yellow part, say that this was at level 6, and then you suddenly increase to level 7. The number of M2L calculations for that one level down, there are 8 times more blue boxes to calculate for. The number of red boxes that interacted with each blue box doesn't change. It's just that the number of blue boxes that you need to loop over in the whole bottom level, because you'll have 8 times more boxes in the bottom level. You'll have 8 times more boxes to calculate. So this yellow part increases 8 times. It just goes like this. But the P2P decreases because you'll divide this into smaller boxes. Actually, the size of each box will shrink into like 1/8 in 3D. And the number of particles inside them will shrink 1/8. So if you follow this blue line, it would have gone quadratically to like here. But it increases 1/8 to down here. So this balance between increasing this 8 times and decreasing this 1/8 has to happen at the right timing, because the P2P is increasing n squared, but this one is only increasing order n. No, this one is not increasing. It's constant if you don't change the level. So the yellow part, unless you divide the tree, remains constant, but the blue part keeps growing n squared. So at some point, you need to change. But then the yellow part increases 8 times and the blue part decreases 1/8. So if you do this at the wrong timing, so say that you switched this level and the yellow part increased this much over here, the timing would still be like this big. So you'll have a huge jump in the timing. Or in the other case, if you didn't divide the tree early enough, this part will keep increasing. So the blue part will become so big, and the yellow part will remain the same. So you'll have like a very thin yellow line and a very, very big blue line. So the key to achieving order n in fast multiple methods is to subdivide the tree at the right time. And how you achieve that is usually assigning a constant number, like a threshold. So say that if the number of particles at the leaf box becomes more than 32, subdivide. And then as long as that number 32 is correct, it will subdivide every time that number increases past 32, it will subdivide. And then it gets subdivided into 1/8, so you'll have 4 particles on average per box. And then that 4 keeps growing, like 4, 10, 11, up to 32 again. Once it passes 32, then it gets subdivided to 4 again. So if you write in your code if statement that says if the number of particles per leaf box exceeds a certain value, then subdivide. As long as you have that, this switch should happen automatically. You don't need to manually program in your code the correspondence between n and the number of levels. You don't need to write such a thing. All you need to do is keep like a threshold for how many number of points you want per leaf box. That's one number that you need to assign to the code, and then this subdivision will happen at the right timing automatically. So that's sort of the timing balance. You can see from this picture also that M to M, L to L, L to P, P to M, these other parts, you don't really see the colors in this plot. They're very small, actually. The majority is either in P to P or the M to L at the bottom level. That's usually the most significant parts of the FMM calculation. So when you want to optimize your code, keep that in mind, because optimizing this part or this part of your code doesn't really give you any speed up, because it's not taking any time, as you can see in these plots. There's no orange or red part. Well, it's very small. You can barely see it. Okay, so I think we are done with the lecture part, and we'll have another 10-minute break, and then we will start the hands-on session, so actual coding. Does everyone have a laptop? Everyone has some environment to program? And I think you will be logging into some server somewhere. Okay, so yeah, I will be showing in the hands-on session, I'll show on this screen my my terminal, so that you can actually see what I am coding. So yeah, I'll do the hands-on session like this. So I will write code here while trying to. So this is like a live coding session for me, starting from this one. So we will try to code this one starting from here, and I think some people are very advanced, but some people are still beginners in writing code. So I will write in C language. You can write in whatever language you want, but if you're not too sure, and if you just want to, copy what I'm doing, then you can also write in C. And I will try to do this in very small steps, so very slowly. I will show you how, well, maybe in the beginning I should show how to set up the environment and make sure everyone is able to run something. But this, I think, is a very good place to start, because it's very simple. It's probably going to be a few tens of lines of code anyway. And it actually gives you the chance to confirm that it's correct. So if you have a bug in your code, you'll know, because the answer will be totally wrong. So I'll go around, confirming that everyone has a working version of this one before I move on to further ones. Because everything starts from here. And as I've explained in the lectures, this is already a good first approximation for FMM. Everything else from here is incremental. So you can change your code gradually and keep saving if it works, so that you don't break anything. Okay, so should we have a 10-minute break before? Okay, so we will start the hands-on session from 11:25. Okay, thank you.